I'm Takeshi Furuichi, a fourth-year master's student at Keio University in Japan. Let me start my presentation titled Developing Gesture-Based Input Techniques for Earrings. In recent years, devices such as hearables and smart rings have been increasingly integrated into daily life. Along with this trend, the demand for devices with a discrete appearance and input actions has been growing. The objective of this study is developing input interfaces using earrings. Earrings have a high level of social acceptability. They are widely recognized as fashionable accessories and are also natural to wear in various situations, such as conversations, meetings, and parties. In this research, to account for differences in shapes and characteristics, we focus on three types of earrings. As earrings come in various shapes due to their fashionability, and we aim to address these variations. The bottom right video illustrates an application scenario where music control is achieved through gesture input using each earring. Many everyday accessories have been transformed into devices. Examples include hats, hair extensions, and masks. Transforming existing items into interface is considered beneficial because the appearance of wearing the device is socially accepted. The positioning of the study focuses on gesture input by touching the earrings. I will introduce two studies related to earring devices. The first study focuses on recognizing facial gestures using earrings. A limitation of this approach is that input based on facial gestures tend to be conspicuous. Our study enables input through the natural actions of touching earrings in daily life. The second study explores gesture using jewelries. Its limitation includes that gestures were designed by researchers rather than users. Additionally, it only proposes gestures without actual implementation. In our study, the gestures were user-defined, and a device for gesture identification was also implemented. The flow of our study is divided into two main phases: gesture exploration and gesture identification. In the gesture exploration phase, the focus is on the investigation of gesture preferred by users. By allowing users to construct gesture set, this study aimed to design a more user-friendly interfaces. In the gesture identification phase, there were three main phases as follows. First, implementation of hardware based on the result of gesture exploration. Second, implementation of gesture identification software. Finally, performance evaluation through user experiment. By implementing a user-defined gesture set and evaluating the effectiveness of that system, this study provides insights into the use of earring as an interface. This is the overview of the gesture exploration study. The objective of the experiment is to conduct a survey of gestures defined by users. The participants were asked to devise gesture using three types of earrings. The final gesture set is decided by majority vote. There were 20 participants in the experiment, and the target actions presented to the participants are shown in the table on the right. This is the result of the hanging earring experiment. The largest number of gestures groups was observed due to the complex mechanism among the three types of earrings. The final gesture set includes 11 types, which consist of gesture groups such as tap, flip, or glide, and twist. This is the result of the surface earring experiment. The gestures are limited due to the earring being fixed. The final gesture set includes 8 types of earrings, including tap and swipe. This is the result of the poop earring experiment. Although there were few gesture groups, it has the largest variety of gestures, as both the gesture groups have directionality. The final gesture set includes 12 types of gestures, consisting of gesture groups such as swipe and pinch and grab. This is the gesture set list. The characteristics of the decided gesture includes operations that use the fingertip, intuitive operations involving directions, and simple operations with minimal motion and operation time. Let me explain the implementation of the hardware. The device was designed to be capable of identifying the defined gestures. First, for the hanging earring, a 9-axis sensor was used to capture the swing and movement of the earring. Next, for the surface earring, a photoreflective sensor was used to detect the contact point on the surface of the earring. Finally, for the hoop earring, a capacitive touch sensor was used to detect contact point along the ring of the earring. This is a software implementation for data collection, the data acquired through Arduino. The system recorded data was for a specific number of frames as follows. For the start timing of the gesture data recording, 2 methods were adapted depending on whether gesture detection was feasible. This is the software implementation for gesture identification. Machine learning was used for this task. The feature extraction process is as follows. First, the time series data from sensor is divided into 5 blocks based on the dimensions of the sensor. Then, for each block, 5 representative values are calculated. These values are used as the features for gesture identification. For the algorithm, 3 models were tested, and the random forest model was selected because it proves the highest accuracy. This is the overview of the gesture identification experiment. Gesture data was collected by 10 participants. For the evaluation, 2 types of models were tested, within individual model and between individual model. Within individual model, the data from a single user was divided into training data and test data to identify gestures. In the between individual model, the data from one user was used as test data, while the data from all other users was used for training. This is the within individual model identification result for the hanging earring. The accuracy was 83.6% on average. As shown in the confusion matrix on the right, both detections between specific gestures can be observed. Specifically, the flip forward, backward, and or glide left, right, and up gestures were falsely detected. From this, it can be concluded that the direction of movement cannot be identified with high accuracy, but the types of movement can be identified. This is the within individual models identification result for the surface earring. The accuracy was 96.6% on average. As shown in the confusion matrix on the right, all gestures have similar accuracy. The insight gained from this result is that gestures that involve touching the surface have high reproducibility. This is the within individual models identification result for the foot earring. The accuracy was 87% on average. As shown in the confusion matrix on the right, gestures that involves moving earring itself have low accuracy. From this result, it can be concluded that it is difficult to capture the movement of the earring through contact with the finger or cheek. The potential solution to this issue could be to add sensors to improve detection accuracy. The figure in the lower right shows the result of the between individual model. The accuracy was are shown below. Across all earring designs, the between individual model exhibits lower accuracy compared to the between individual model. This performance decline is attributed to individual differences in gesture performance among users. By incorporating software or gesture definitions that can adapt to these individual differences, it is possible to improve the accuracy of the between individual model. As for the future work, gesture detection is an important area to address. Currently, the hanging earring cannot identify gestures in real time. To enable real-time detection, it will be essential to distinguish gestures from swing caused by walking or other everyday activities. Appearance should also be improved. Considering practical use, it will be necessary to implement wireless functionality and integrate sensors and batteries into the device. This is the summary of the presentation. Thank you for your attention.